Hello and welcome. My name is Mahan. I'm a graduate student at Georgia Tech. Today I'm going to be presenting a paper leveraging software-defined networking for incident response in industrial control systems. Here you see the authors for the paper. Would just like to acknowledge them and say a big thank you for allowing me to use this paper to produce this presentation. A link to the author's paper at the IEEE website can be seen here at base, and you can follow that over to the IEEE website and download the paper if you would like to have a look. A quick note on the authorship. This presentation is a presentation put together over a research paper for a graduate course and is in no way meant to be interpreted as my own material. There are many places throughout this presentation where I quote the authors directly. At first I had that set up where I quoted each of them and sourced it, but since the whole point of this presentation is to present the author's work, I decided to take those out because they were really disruptive. Where you do see quotes is going to be where I'm quoting other sources. There are media sources, news sources, and then also sourced photographs and other things that I use. At the end of this presentation, there is a resource page which will have helpful links. Again, the link to the author's paper can be seen at base. And if you want to view any of the reports that were quoted or any of those articles, again, there's a resource page at the end of this presentation. So the bottom line of the paper is that software-defined networks and network function virtualization can facilitate automatic incident response to a variety of attacks against industrial networks. The combination of SDNs and NFVs show promise in providing novel defense-in-depth solutions for industrial systems. So what are software-defined networks? They are a centralized approach to the management of network infrastructure in which the underlying network infrastructure, rather than being traditional on-wire infrastructure, is abstracted from the applications. The network function virtualization allows for open source software to be used over proprietary infrastructure. So this paper looks at the problem space represented by critical infrastructure being controlled by these industrial control systems. And since in looking at the elements of security, industrial control systems are predominantly concerned with availability, they're often very vulnerable to different kinds of cyber attacks. These cyber attacks obviously result in large economic losses and potentially could lead to major loss of life. As the authors point out, although several mechanisms to detect attacks have been developed, there's little work being done on how to automatically respond to these alerts. Most responses are manual or hardwired. Think of failover switches and something like that. The goal of the authors was to design an incident response policy to reconfigure the network and mitigate the impact of an attack. There are a couple of qualifications the authors point out. One, they do point out that they are not covering how to design or create an intrusion detection system. The authors assume in the scenarios that are presented that a intrusion detection system exists and that it has the capability to alert the SDN controller that they propose using later in this presentation. They also assume the adoption of Ethernet-based industrial protocols versus old analog legacy infrastructure. So what is the big deal? What is at risk? There's a few examples the authors point out. I added in one or two of my own. But if you see here, there was the Rye Brook Dam incident just outside of New York City. Just a small dam, nothing major. However, it was controlled by an industrial control system. And apparently Iranian actors were able to get into the industrial control system network, which controlled the dam and could manipulate the system. Now this dam, very small, used to control flooding on this Rye Brook. However, it's only a matter of scale. So if you can imagine attackers looking at a small dam like this, it would be the same process, although I'm sure with there's more security, one would hope, in thinking of something like Hoover Dam or something along those lines. One example that the authors point out was the loss of power in the Ukraine power grid. This was in 2015. Russian actors took down power systems which caused a blackout for more than 200,000 customers. This image is not of Ukraine. This is an image of Manhattan during the blackout, but it just illustrates what having a huge city, in this case like Kiev, might be like to be completely blacked out. There are many articles on the Ukraine power grid takedown. I believe In-Destroyer Crash Override is the name of the malware, and you can read more about it. Again, there's resources at the end of this paper. In this example from just last year, 2018, the US government revealed that it had found Russian intrusions into many industrial control systems, networks, energy, nuclear, commercial facilities, water, aviation, and critical manufacturing sectors. In fact, it said that there had been 137 types of interfaces between grid systems that have been compromised. Obviously, nothing major has come out of this. We haven't had any major events, but it shows the level of risk that these industrial control system networks present. So now let's look at some of the advantages of software-defined networks and network function virtualization as pointed out by the authors. First though, let's cover some of the disadvantages according to the authors of legacy networks. So in these industrial control systems, you have proprietary hardware and software. Some of the hardware beyond the programmable logic controllers, the sensors, the switches, etc., are what the authors call middle boxes. These are dedicated hardware devices. Think of them as the HMIs that operators would use to interact with traffic on the network. So you can think of a human-machine interface where a smart interface where an operator can visualize what is going on in a network and then can input to change what is happening or input to set new values, etc. All of that takes a high capital investment. So if you have a company such as Schneider Electric, Honeywell, etc., one of these major companies that comes in and builds your architecture for you, they are supplying you not only with sensors and everything, but also these middle boxes for monitoring everything. And then that goes into the next problem, which is the difficulty of deploying new services because of the need to reprogram or reconnect the middle boxes. And so you can imagine if you design something large like a power plant, and that power plant is designed to do one thing. And then if you decided that you wanted to pivot or to add services or do something in a slightly different way, the likelihood is that you're going to need to involve that same provider, who would we say, Honeywell or Schneider, whoever. You have to involve them in either building new architecture or in dramatically changing some of the devices So here we see a really basic loop in which you have a PLC which is sending values to this actuator. The actuator is then doing stuff, we'll say, which causes this process to take place. This process puts out feedback. The feedback is then read by a sensor. The sensor sends the feedback, and the feedback's routed back to the PLC and also is observed by the supervisory network. The supervisory network can then adjust based on what it's seeing and send values back to the PLC, which can then adjust the actuator, which would then adjust the process. It's a very simple, straight kind of out of a textbook. But again, it's important to point this out so that you can see how the SDN controller and sort of an SDN switch can fit into the scheme of things. So the authors put an SDN controller here. The SDN controller, again, you have to imagine that it is interacting or can interact as needed with an intrusion detection system, which can, is embedded all over the place and can monitor what is going on. So in this case, same thing, information is just being dual routed at the end to the supervisory system, and then also the SDN, software-defined network. The authors point out, again, in the advantages that software-defined networks and network function virtualization can be integrated with industrial control networks at both the supervisory and field levels. And they enable the deployment of different defenses without modifying the legacy system. So in this case, this was actually changed out and then this was added. But otherwise, the rest of the network infrastructure stays the same. And now let's look at an actual scenario. So in this scenario, the authors imagined that an IDS has detected an attack. The IDS, we have to put it here, it's not illustrated in here, but the IDS alerts the SDN controller. The SDN controller then sends commands to route the attack traffic to the honeypot. Now it's important, as the authors point out, that the honeypot needs to really emulate this whole control loop. If it doesn't emulate it, then the attackers are going to know that they have now been pushed out of the original industrial control system network that they were trying to invade. And I say they, it may not be a person attacker, it can be malware, etc. But as long as the honeypot emulates the control loop correctly, likelihood is that the honeypot and the SDN and the administrators, etc., will be able to get a very good idea of what the malware or what the actors are intending to do. So this is their first proposed scenario. So in the second proposed scenario, the authors imagine an attack takes place, and the attack compromises this sensor. Now, again, you have a situation where it's the IDS and not the SDN, but the IDS that the authors assume is in place sends an alert to the SDN controller. The SDN controller has a predefined action that it's supposed to take in the case of a sensor being compromised. And in this case, it has this little box right here represents memory internal to the SDN that then simulates this compromised sensor. It sends, obviously it's not actually sensing what's coming out of the process now, but it knows estimated values that should be in place were the sensor acting correctly. and then it sends those estimated values back down to the PLC, which can then keep the actuator running in normal values, which will then keep the process running in normal values. The authors do point out that this has to be a temporary solution. You can't go with only estimations for a long-term process, because then you're not actually sensing what is going on out here. But it will help mitigate either an attack or even a damaged sensor, and allow for the system to run normally, at least again for a short period of time, until the sensor can be either repaired or the attack can be averted, etc. In their third proposed scenario, the authors imagine a system that is not necessarily attacked, but is just has a failure. So in this system, you have a redundant system here. This is the normal system here. And this PLC and actuator, something happens and it seems like they're not functioning correctly. What happens is this sensor is going to send back a reading that says, hey, this sensor is functioning correctly, however, I'm not getting the value I'm supposed to get here. In this case, much like a failover switch would happen, but the SDN can act as that failover and then can basically bring online this backup system. And when the backup system back online, in the very near term, this sensor would start receiving correct values. And again, it can run in this fashion as it's supposed to, as a redundant system, while either repairs or mitigations are put in place to fix the PLC and the actuator. So the authors put together a prototype. It follows basically the second scenario that they had before. It did have a couple of qualifications, and I think it's worth reading through these just to make sure that everyone's tracking. So the intrusion detection system instance always receives a copy of the information reported by sensor LIT 101. It uses a mathematical model to identify differences between sensor readings and estimated values. If the difference is greater than a given threshold, the IDS notifies the SDN controller. Then you have the SDN controller following its prefigured incident response policy. If you remember the second scenario that we covered, it was stated there that the SDN controller had a prefigured incident response that it would put into place as soon as it detected, in that case, that compromised sensor. So same thing going on here. And then the SDN controller modifies the flow table of the SDN switch to perform the configured response. And then finally, the plant is controlled by estimated values, if it all works. So it's all fine and well to say all that, but what did the authors do about it? So the authors put together an experiment in which they put together a virtual environment. They used mini CPS to put together a VM, and the mini CPS extended Mininet, which is a light virtualization environment tailored for SDN experiments and emulation to support Ethernet IP as an industrial network protocol. And again, so that's another assumption that this experiment makes. It wasn't covered in the last, but the assumption is that Ethernet over IP is being used here. So in the simulation, the attack compromised this sensor such that it would only ever report a fill level on this tank of 0.3. So remember, this tank is supposed to be filled between 80% and 50%, and it's supposed to go up and down at that level between there. But now this sensor is going to say, no, I'm only at 3%. So, or 30%, I should say. So the tank's going to stay at 30% according to this sensor, which is going to cause the tank to overfill It'll also not allow for the valve to be open, and it will keep the pump closed, which means that this tank 301, which is downline, is never going to get filled. So we got this tank overflowing and this tank staying empty. So what happened? With the experiment outcomes, you can see that the experiment ended favorably. You have the normal operation, and again, it's between here and here. This is just showing that the tank fill level stays between 0.5 and 0.8, so between 50% and 80%. That's the viable range that the tank is supposed to stay at. If the compromise had been successful, then the tank would have gone to overflow level. But instead, the SDN ran its simulation. The simulation sent estimated values, which said, hey, this should stay between these basically 3%. So it allowed it to go up 3% and then to drop 3%, and up 3% and drop 3%, which saved the tank and averted catastrophe, especially in the case that things would burn up, say if tank 3, which is down the line, could not ever fill up. But in this case, crisis averted, estimated values in the SDN did win out. So that's it for the authors. The conclusion really is that they only tested it virtually. Obviously, it hasn't been tested large scale, but they have successfully shown that the software-defined networks and network function virtualization can mitigate an attack and can put into place an automatic response to an incident. This, according to the authors, is the first implementation of SDNs and NFV for incident response, and they do encourage others to extend the work that they implemented. And I would just like to say thanks again to the authors for allowing me to use their material. Finally, we have the resources page. I encourage you, if you're interested in any of this, to go take a look at these. There's many other industrial control system hacks out there that are very interesting, and I encourage you to read up on them, see the value that something like software-defined networks and network function virtualization can do to mitigate the disastrous results of some of these attacks. And that's my presentation. Thank you for your time.